part, what we'll be discussing about one common roof that Maxwell brought all the relations, for example, the Gauss law, Faraday's law, Ampere's law, into one common roof known as the Maxwell's law. These are relations which are in integral form. So when we say that these are relations in integral form, that all the relations are given in the form of integration, because there is also a differential analog possible for this. Right? Now coming back, Maxwell's first relation basically is nothing but the Gauss law. So if you have a single charge which is present in a particular vicinity, as a result there is going to be some electric field produced. In the same way, we talk about the case of magnetic field, that relation is equal to 0 on the right hand side. Reason being, there are no magnetic monopoles. Then there are Ampere's law and the Faraday's law, which basically relate the circuitous motion of the electric field and magnetic field. So what did Maxwell do into it? The Maxwell added a term which is known as a displacement current. Displacement current is proved to be very essential to understand about the fluctuating values of electric field and magnetic field. So stay tuned into this particular chapter, listen to it very carefully, you'll get to know the origin of the displacement current. So now we begin on with the next part, that is the Maxwell's equations. So let's try to understand about the Maxwell's equations. We are aware about the few different equations which we are aware, like the Faraday's law, the Ampere's law, the Gauss theorem, and so on, right? So Maxwell basically combined all of that and wrote down the equation like Maxwell's equations. So from the Maxwell equations, it was very easy to identify what should be the equations which are going to satisfy all of these, yeah, the wave equations which are going to satisfy exactly all the equations which were defined by Maxwell's. So let's go further and try to identify. So here, when we talk about the electricity and magnetism, all of that can be combined together to form the electromagnetic waves. So here, when we talk about this, the first equation that we know is the Gauss law. So Gauss law tells us that it's basically if any particular region has a charge enclosed in it, then the electric field in that particular vicinity can be found from this particular relation, that is integration of E dot ds is equal to Q by epsilon naught. So this is the Gauss law for electricity. But we are completely aware that we can have a standalone positive charge and a standalone negative charge, right? So these charges can exist on their own. As a result, the Gauss law exists for both positive charge and negative charge. It's just that the direction of flux changes. But for the case of magnetism, there is nothing like a standalone positive charge or standalone negative charge. There are no standard charges. Yeah. So there are no magnetic monopoles to be precise. So if there are no magnetic monopoles which exist, so for the case of magnetism, the total magnetic field over a given area, that is, this is the case. So since there are no magnetic monopoles which exist, so total magnetic field over a given area, if you just try to find out over the total area, that is going to be equal to 0, because there is no single charge, no single magnetic monopole existing. Going further, if you talk about the Ampere's law, Ampere's law is basically B dot dl, that is equals to mu naught into I, which we are aware of it. Yeah. In addition to that, what we do, we add a factor of d phi by dt. So when epsilon naught d phi by dt, so when we add that part, so that gives rise to the extra bit, which is the displacement current. So here comes the displacement current. Yes, in an analogous way, the variation, so it should actually be equals to, this should actually be given by E dot dl. So if I talk about E dot dl, so this is going to be equals to mu naught I, plus there is going to be the variation, the flux variation in terms of the electric flux. So one is going to be in terms of the magnetic flux, other one is going to be in terms of the electric flux. So combining all of this together gives rise to what are known as the Maxwell's equations. Let's go further from here. So what exactly are the Maxwell's equations? So we have already written them down. We know that when we are in vacuum, there are no single charges and therefore there are no conduction currents. So the Faraday's law and the Ampere's law take the form like normal E dot dl, which is equals to minus d phi b by dt. So this is the equation, and for the case of Ampere's law, so B dot dl, which is equals to the displacement current that we are aware of. So as a result, if you just try to put in the equations, so for the case of electric field, so let me just try putting in here. So let's say this is our y-axis, this is our x-axis, sorry, z-axis, and let's say this is our x-axis, right? Now let's try to identify and talk about the different waves that are there. So if you talk about for the case of electric field, so the electric field waves vary like this. If you talk about for the case of magnetic field, so for the case of magnetic field, the magnetic field waves are going to vary like this. So as you see, the oscillations are taking place along perpendicular directions like here and here. So electric field is oscillating along the y-axis, magnetic field is oscillating about the z-axis, but both of them are propagating along the x-axis. So that is the most important thing to be understood. And both these equations actually come from these two equations, which are as a result of the Maxwell's relation itself. So the wave described above propagates along the positive x direction, the electric field remains along the y direction, and the magnetic field along the z direction. The magnitudes of the field oscillate between this and this. So again, let me come here. So you see that, let me change the color. So here the maximum magnetic field value is going to be equal to B naught. Similarly, this value is going to be equal to minus B naught. If you talk about for the case of, if I talk about for the case of electric field, so this is going to be E naught, and similarly this is going to be equal to minus E naught. So this is how the electric field and magnetic fields actually oscillate with time, right? So in this case, as we see that there is a polarization taking place. So what does that mean? The electric field vector is only going to be polarized. So if I just say that this is my y-axis and this is my x-axis, so the electric field vector is only going to be polarized along this direction. There are no other oscillations taking place. That is, if I just have to say, so these are the oscillations taking place for the electric field vector. No other oscillations are there. In the same way, if we talk about the magnetic field, so for the case of magnetic field, we'll have something like this. So here, this is z-axis, this is my x-axis. These are the oscillations that are taking place. So if these are the oscillations that are taking place here, it's again going to be only along z-axis. So again, it's a polarized light that you have. So it's linearly polarized along the along the y-axis and the z-axis respectively, right? Okay, so let's move ahead further. Let's now try to understand about the Faraday's law. If we have to understand the Faraday's law, so what exactly we are going to discuss? Because we have already got to know about what is the expression of the electric field and the magnetic field, right? How exactly it propagates, what direction it oscillates. So based on that, if we now have to understand about the Faraday's law. So Faraday's law basically takes into account the circulation of the electric field. So if we talk about circulation of the electric field, we know that the electric field is oscillating along the y-axis, okay? So let's take a rectangular cross section or rectangular path, let's say ABCD, okay? So this, it's oscillating along about the y-axis and about, it's moved along the x-axis. So the rectangular path is in the xy plane. So if I take xy plane and I take a small cross section here which has a thickness, let's say dx. So as a result, what direction if I have to talk about the circulation is basically going to be an integral of E dot dl. So this integral is going to point along the z-axis. So let's try to understand what direction, what is the net result going to be. So E dot dl, if you break it out, so from A to B, B to C, C to D and D to A back, okay. So A to B E dot dl, here the electric field, the oscillation of the electric field is along y-axis and it is being, the distance is being covered along the x-axis. So obviously the dot product is going to be 0. The first term goes to 0. Second term, the electric field and its movement, the circulation, both are along the same direction. So it is positive, so it becomes E, and it is going to be a function of the point from where we are trying to find out. The electric field is going to be function of this particular distance. So E is going to be function of x2 into the length. So if I say this length is equals to L. Going further from C to D, again, since the electric field is oscillating along y-axis, the circulation is perpendicular to it, so this does not yield anything. Then the next one is basically should be between D to A. Yeah, so it is D to A, sorry. So if it is D to A, obviously the electric field is going along positive y-axis and the circulation is taking place along negative direction. So this results into negative, and it's also going to be a function of x1. x1 is nothing but A, x2 is nothing but B. We'll just be substituting that. So as a result, if we get it, so we'll get Ex2L minus Ex1L, right? So if we substitute that, so we'll get E naught L sin omega t minus x2 by c minus sin omega t minus x1 by c. So this is going to be the expression. But let's go further and try to find out the flux. So for finding the flux basically flux lines are going to go perpendicular to the area, right? So for finding out the flux lines, what will we say? Let's say phi p represents the magnetic flux. So as a result, B is the magnetic field into the area. Area is what? That strip. Let's go back here. So here, if you see, this length is L, this total length is L, and the strip has a thickness. This thickness is equals to dx, right? So the area of this particular strip is going to be equals to the magnetic field into the area, that is going to be L into dx. As a result, if we write it, so we'll get B naught sin omega t minus x by c, that is the general expression of the magnetic field, into L dx, and this is taking place along the z axis. Okay, so phi, the total flux, here you are going to integrate from x1 end to the x2 end, the two extreme, that is point A to point B. So if we integrate this expression, so sin omega t minus x by c, so if we integrate, obviously the first expression term is going to give me minus cos omega t minus x2 by c plus cos omega t minus x1 by c. So if I just rearrange this equation, so at rearranging this equation, basically this gives me the flux, and now if I differentiate it, so if I differentiate, what exactly happens? The coefficient of t is going to come out. So when the coefficient of t comes out, effectively you get the differentiation of minus cos is going to be sine, and omega is going to come out, so the omega here gets cancelled. Yeah, so when that happens, this becomes sin omega t minus x2 by c minus sin omega t minus x1 by c. So we have got to this particular expression. Also, if you see here, we had an expression like this. So this was the integral of, this is the integral of E dot dl. So we have E dot dl here, and we already know that E dot dl equals to minus d phi by dt. So using these two equations, what we get from here is that the maximum value of the electric field is related to the velocity of light into the maximum value of the magnetic field. So E naught is going to be equals to c, that is the velocity of light, into the maximum value of the magnetic field. Yes, so this is an important conclusion that we derive from the Faraday's law. Okay, let's go further and talk about the Ampere's law. So what is the Ampere's law? Ampere's law is nothing but B dot dl equals to mu naught I, right? So mu naught I we are talking about in the vacuum, let's say. So in vacuum, if I talk about, that is, there is nothing like the two plates where there is a varying electric field. I'm not talking about that. So let's talk about this. Here, like in the case of electric field, we'll take a cross section. Here, let's say E, F, G, H. In this cross section, we need to take a small thickness, let's say dx. And here, point E corresponds to x equals to x1, point H corresponds to x equals to x2, right? So as a result, what will we get? So the circulation in the same way like for the case of electric field, we'll get E to F B dot dl, then F to G B dot dl, G to H B dot dl, H to E B dot dl. So the first one, if you look at it, here the dot product, E to F. So E to F basically is along the same direction as the direction of the magnetic field. So this results. F to G is going to be 0, the dot product is going to be 0. G to H again is going to be with a negative sign, H to E is again going to be 0. So if I put that all together, so I'll get B to x1L minus b into x2L. So let's put all of that into an expression. So we'll get b naught L sine omega t minus x1 by c minus sine omega t minus x2 by c. Just simply putting in the expressions of x1 and x2. Right? The expression is b dot dl, which is going to be equals to mu naught epsilon naught d phi e by dt. Yeah. So phi e, that is the electric flux. Electric field, we will be doing the same thing like we did in the case of Faraday's law. So we'll be integrating over that small strip. So if we integrate over that small strip from x1 to x2, that length, the vertical length was equals to L. So if we integrate it, again we are going to get an expression like c by omega e naught L minus cos omega plus cos omega this. So from here, if we differentiate, obviously minus cos omega goes out in the form of sine omega, and because of this, when you are integrating it, so you will get an expression of minus c e naught to L. We know that, okay, so this should have been d phi e divided by dt. So using this expression, so if I just compare the two expressions, so I'll simply get, here you see c e naught L, and from there you get b naught into L. So if I just use these two expressions, I'll get something like this. So E naught by B naught, I already know that E naught is equals to C times B naught. So if I substitute it here, so effectively I'll get E naught as C B naught, so B naught and B naught goes off, so you are left with just 1 by C square. So as a result, C is going to be defined as 1 by square root of mu naught into epsilon naught. What is mu naught? Mu naught is the permeability of free space, epsilon naught is the permittivity of free space, right? So these are the equations that we get. So the velocity of light is defined in terms of the permeability and the permittivity. Okay? So this is what is we get out of it. Hopefully you understood this, that we get two equations, that E naught is equals to C times B naught, and the speed of the wave is given as 1 by, basically this is the velocity of light, so it's going to be equals to 1 by mu naught into epsilon. Now there is one simple thing that please understand. We also know that velocity in any medium is defined as C divided by N, right? So velocity is equals to C divided by N. So N is nothing but the refractive index of that particular medium. Also, if you have to define the velocity in any other medium, that's going to be defined as 1 over mu into epsilon. So mu is nothing but, let me write it down. So you'll have the relative permeability mu r into mu naught into, similarly, relative permittivity epsilon r into epsilon naught. So this gives you the equation 1 over mu r into epsilon naught, and here in the numerator you get C. So as a result, the diffractive index of any particular medium, that is given as something like mu r into epsilon naught. Okay, so hopefully you understood till this point. In the next part, we are going to discuss about some problems related to this. In these Maxwell relations, we got to know about what exactly is the common factor between all these relations that we get to know. Further from there, we also figured out what exactly is the displacement current. Why do we need it? And when we put in the displacement current, how exactly that displacement current is going to help us later on in figuring out the Faraday's and Ampere's law, and going further from there, figuring out a relation for the velocity of light as well as the relationship between the maximum value of electric field and the magnetic field. So stay tuned for the next part, where we actually try to discuss about the Faraday's law and the Ampere's law, and try to understand about how exactly these relationships actually help us in getting the values of the speed of light in a vacuum, as well as the relationship between the maximum value of electric field and the maximum value of magnetic field.